Newton's theory said that the force was instantaneous. He has to modify Newton's laws. They have very small effects, these modifications. One of them is all masses fall. Light has energy, and energy is equivalent to mass, so light should fall. And that should mean that light going near the sun is deflected. It is. And also the force of gravitation is slightly modified in his theory, so that the laws slightly change, very, very slightly, and it is just the right amount to account for the slight discrepancy that was found in the movement of Mercury. Finally, with connection to the laws of physics on a small scale, we have found that the behavior of matter on a small scale obeys laws so different, very different than things on a large scale. And so the question is, well, how does gravity look on a small scale? What is called the quantum theory of gravity? There is no quantum theory of gravity today. People have not succeeded completely in making a theory which is consistent with the uncertainty principles and the quantum mechanical principles. I'll discuss these principles in another lecture. Now, finally, you will say to me, yes, you told us what happens, but what is this gravity? Where does it come from, and what is it? Do you mean to tell me that the planet looks at the sun, sees how far it is, takes the inverse of the square of the distance, and then decides to move in accordance with that law and move? In other words, although I've stated a mathematical law, I haven't given you no clue as to the mechanism. I will discuss the possibility of doing this in the next lecture, which is the relation of mathematics to physics. But finally, in this lecture, I would like to remind, just at the end here, to emphasize some characteristics that the gravity has in common with the other laws that we have mentioned as we passed along. The first is that it's mathematical in its expression. The others are that way too. We'll discuss that next time. Second, it's not exact. Einstein had to modify it. We know it isn't quite right yet because they have to put the quantum theory in. That's the same with all our other laws. They're not exact. There's always an edge of mystery. There's always a place that we have some fiddling around to do yet. That, of course, is not a property, probably not a property. It may or may not be a property of nature, but it certainly is common with all the laws as we know them today. It may be only a lack of knowledge. But the most impressive fact is that gravity is simple. It is simple to state the principle completely and have not left any vagueness for anybody to change the ideas about. It's simple and therefore it's beautiful. It's simple in its pattern. I don't mean it's simple in its action. The motions of the various planets and the perturbations of one on another can be quite complicated to work out. Or to follow how all those stars in the globular cluster move is quite beyond our ability. It's complicated in its actions, but not in the basic pattern or the system underneath the whole thing, as that's a simple thing. That's common in all our laws. They all turn out to be simple things, although complex in their actual actions. Finally comes the universality of the gravitational law, the fact that it extends over such enormous distances. That Newton, in his mind worrying about the solar system, was able to predict what would happen in an experiment of Cavendish, where Cavendish's little model of the solar system, the two balls attracting, has to be expanded 10 million times to become the solar system. And then 10 million times expanded once again, and we find the galaxies attracting each other by exactly the same law. Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry. Thank you.